These new methods include, but not limited to, the binary inversion, multinary inversion and the joint inversion approach. In some application of gravity imaging such as subsurface tunnel detection, salt structure imaging, the density range of the target and the density of host rock are usually well known or well constrained. However, the conventional inversion in this case will still produce a diffusive image with spread density ranges and continuous model space. In reality, the inverted density value should be clustered nearby the density value of the host rock and the density of the target. In the case of a model with two distinct density values, the continuous inversion parameters min the original model space can be transformed into a new binary space for inversion. Zhdanov and Cox introduced a multinary inversion approach for geological models with more than two density values for different geological units. Several different functions, such as Heaviside function and Gaussian function, can be used for multinary transformation. Within the framework of multinary approach, the value of the inverted model parameters is enforced to be nearby the vicinities of the preselected values. As we know that each geophysical method and data is only sensitive to specific model parameter. Due to the inherent non-uniqueness of geophysical data inversion, the recovered model parameter from individual inversion can be ambiguous. Such ambiguity can be reduced by incorporating more a priori information into the inversion. Different geophysical models can be coupled with each other either directly or structurally. For example, the density and seismic velocity can be related with each other by empirical equations. Alternatively, a density model can be related with the velocity model by assuming the structurally similarity. As a result, it is possible to enforce the coupling between different model parameters by inverting this different geophysical data set simultaneously. The structurally similarity-based joint inversion can be achieved by minimizing the cross gradients between different model parameters. Within the framework of this approach, the structural similarity, between model parameter M1 and M2, can be measured by the cross gradient, which is defined as follows. Such regularization term will be minimized during the minimization of data misfit functional for the joint inversion approach. Zhdanov proposed a new and more flexible joint inversion approach based on Gramian constraint. Within the framework of this approach, different model parameters are coupled through the Gramian matrix, which can either force the direct relationship between different model parameters or their spatial gradients. One good property of such joint inversion is that the algorithm will only enforce such coupling when it does exist and will not introduce artificial coupling when there is no relationship or coupling between different model parameters. It is straightforward that the joint inversion formulation can be simplified if there exists a shared model parameter for different geophysical data set. For example, the DC electric method and the magnetotelluric mount method both invert for the electric conductivity. As a result, it is unnecessary to formulate the joint inversion using the approach that we have just discussed, in this scenario. Based on this idea, the joint inversion for depth to basement using different geophysical data can be greatly simplified by considering that the depth to basement is a shared model parameter for different data sets such as gravity and mount data. In the meantime, each method may also have a private model parameter such as density contrast for gravity data and conductivity contrast for mount data. Here we consider a synthetic sediment basement interface model. The synthetic gravity and mount data are simulated on the Earth's surface for this model. These data will be used to recover the sediment basement interface. Furthermore, we assume that the density contrast value and conductivity contrast value are also unknown. Under this circumstance, the inversion of individual data set is characterized by strong non-uniqueness. By assuming the shared model parameter of depth to basement, for gravity and mount data, during the joint inversion approach, the recovered model parameters is much closer to their true value comparing to the individual data inversion, as one can see in a comparison between separate gravity and mount inversion for depth to basement, and the joint inversion result for a synthetic sediment basement interface model.